Hey friends, welcome back. We're at it again. We've got graph, and we are trying to find these one-sided limits. Okay, so I want to take the limit of f of x as x approaches -2. This negative means from the left, so I'm going to be a little bit less than -2. So I'm coming in from the left, and I notice something. Oh, my y values are going to keep getting bigger and bigger and bigger. So the first time I introduced this, I said, well, we say this is equal to a number if the y values are approaching a specific single value. In this case, the y values keep getting bigger and bigger. They're not approaching any single number, so we said that this limit does not exist. Okay, now that's totally fine. But we're advancing in the world of calculus, and we decide at some point that just saying does not exist isn't always good enough. Why not? Because let's think about the limit as x approaches, let's say, this number 2, right here. From the left, I'm going to approach a certain y value. From the right, I'm going to approach a different y value. Okay. The left one-sided limit exists. The right one-sided limit exists, but they don't match each other. So the limit of f of x as x approaches 2 does not exist, right? I would write this. The limit of f of x as x approaches 2 does not exist. Okay? But this behavior, this vertical asymptote right here, is clearly different from that behavior. And generally speaking in math, we like to increase our vocabulary to address things that are different from each other, right? We just want to describe things better. So we say, in this case, the y values increase. They get bigger and bigger and bigger and bigger. And that's a concept we encountered last time we talked about end behavior. When x got bigger and bigger and bigger and bigger, we used the symbol infinity to represent something bigger than any number. So we would say this is equal infinity, which I want to point out, last time I said infinity is not a number, and I stick to that. Infinity is not a number. So how can you equal infinity? How can you equal something that's not a number? It turns out that in the world of limits, this expression right here, to say a limit equals infinity, is a very specific and technical statement that is not saying the limit is a number. It is not saying infinity is a number. It's saying something super specific, namely, as x approaches -2 from the left side, the y values will get bigger and bigger and bigger in the positive direction. They will go up forever. And that behavior is encapsulated in this statement. The technicalities will come at the rant in the end. Okay, so now let's take the limit of f of x as x approaches -2 from the right. So this is coming from numbers a little bit bigger than -2. Think like -1.99, -1.999. Okay, so I'm coming here and I realize, oh, the y values get bigger and bigger. So I will once again write equals infinity. Is it wrong to say the limit does not exist? No, it's not wrong. This is just a better way to capture this behavior in symbols. So we prefer to say this going forward. Okay. Now, this then raises the question, if I have the left one-sided limit and the right one-sided limit with the same outcome here, does that mean I can write the limit of f of x as x approaches -2 and have this from both sides? Can I write equals infinity? And the answer is yes. This is supported by these two things. With the symbols, with the concept, everything is good. Cool. Now let's take a look as x approaches 1 from the left. So as I approach, this is 1. There's another vertical asymptote there. So I'm going to approach from the left, and my y values are getting deeper and deeper into the negatives. So we will say the limit is equal -infinity. This statement indicates the y values go down indefinitely into the negatives. What if I approach, or what if x approaches 1 from the positive side? So I'm approaching 1 from the right. Oh, this is going to positive infinity. So now, can I look at these statements and say the left one-sided limit and the right one-sided limit do not match? Can I then say the limit of f of x as x approaches 1 does not exist? This is a super correct statement. Now, on technicality, could I also say this limit does not exist? That would not be wrong. But, as you can tell, this behavior and this behavior are not the same as each other. So going forward, we would rather say positive infinity for this kind of behavior rather than say does not exist, and reserve does not exist for cases where we mismatch approaching from the left and from the right. I know this is a bit of a weird thing, and as a student, I wasn't super satisfied by this going forward. It almost felt like I had been lied to, that I was told one thing, and then we decided to change it later. But, okay, a lot of times in math and science, we feed students kind of white lies in the sense that we present something that's overly simplified at first, and then later on we say, okay, but technically, it wasn't that simple, so let's come up with a better framework that addresses some of the more fringe cases. So think of it as one of those things. It's not that we lied, it's that at the time, we just weren't ready, and now is the time to advance the discussion, okay? So, quick recap. If I say a limit is positive infinity, that means as x approaches whatever value is here, the y values go up indefinitely to bigger and bigger positive numbers. If I say the limit is negative infinity, that means as x approaches that number, the y values are going down to deeper and deeper negative numbers indefinitely. Right? If the limits, or the one-sided limits from the left and the right match each other, then I'm able to say the overall limit is equal to infinity if they both go up, or if they both went down, then I could write negative infinity, right? If they both here match to be negative infinity. But if I have a mismatch, as in the left and the right are going to go in opposite directions, then I would continue to say the limit does not exist. It is now algebra time. So we've got a function. We would like to find each of these limits. Okay. So one of the first things we attempt to do when we want to evaluate a limit algebraically is we take this x value and we just try plugging it in to see if we get a number. As in, are we able to just evaluate f of negative 1? Okay. If we can get a number, then oftentimes the thing we're dealing with is going to be continuous at that point, so the graph is going to be connected, and we're just able to say, oh, whatever the y value is for the function, that's just going to be the limit, right? But we see very quickly, if I try to take negative 1 and plug it in to the denominator first. So negative 1 squared is 1, minus 2 times negative 1, so that's positive 2 now. So I get 3, minus 3 is 0. So I have 0 on the denominator. Ooh, dividing by 0 gives me not a number, so I've got a problem. Okay. Now I could try to graph this function and evaluate the limit using the technique in the previous example, but before we do that, let's try to do this algebraically. Okay. So first strategy, as soon as you identify that the denominator can be 0 at any of these values that we're interested in, we want to factor the function just to get some better insight. Okay. So on the numerator, I'm looking for things that add to negative 5 and multiply to positive 6. I'm thinking negative 2 and negative 3, right? That should work. And on the denominator, I'm looking for things that add to negative 2 and multiply to negative 3. So I'm feeling x plus 1 and x minus 3. Okay, and you can FOIL that out and verify that it works. All right, so here's the deal. As x gets very close to negative 1, but a little bit less than negative 1, if I look here, if x is close to negative 1, negative 1 minus 3 is just negative 4. So as long as x is close to negative 1, that's close to negative 4, and that's also close to negative 4. Oh, those are just the same number as each other. I could just cancel them. So I could rewrite this as simply the limit as x approaches -1 from the negative side of x minus 2 over x plus 1. And it's totally legit, right? Because this is a number, that's a number. They're not both 0, so I can just divide the top and bottom by that and be done with it. Okay, so now I look at this and go, all right, on the top, -1, a number close to -1, minus 2, is very close to -3. Okay, this is a negative number, and that's all I care about for now. But on the bottom, if x is very close to -1, that means -1 plus 1 is very close to 0. Okay, but it's not exactly 0, so I'm not dividing by exactly 0. Now it matters, okay, whether x is a little bit less than -1, or as we'll see down here, a little bit bigger than -1. Now, why might that matter? Right, okay, so let's imagine x is a little bit less than -1. So -1.0001, for example. Now, if we take that and add 1, I get -0.0001, right? It's very close to 0, but it is a negative number. As opposed to when x is a little bit bigger than -1. So think -0.999, right? -0.999 plus 1 is equal to positive 0.001. Very close to 0, but it is a positive number. Now, why would this matter? Because on the top, a number close to -1 minus 2 is just always a negative number. It's close to -3. But on the bottom, depending on whether x is less than -1 or greater than -1, it changes whether the denominator is negative or positive. And that's a very important change. Okay. So keep in mind, we're doing this algebraically, but we're still sort of sticking to it conceptually. Okay. The argument here is I have a negative number on top, and I'm dividing by, since x is a little bit less than, that left side limit right there, a little bit less than -1, this number is a little bit less than 0. What's a negative divided by a negative? It is a positive number. But when you divide by something very close to 0, your answer will be very extreme. It might be super positive or super negative. Let's look at examples, right? Let's imagine if I take the number 3 and divide by 0.00001. I get 300,000. That's a huge number, right? But now what if I take 3 and divide by negative 0.00001? I get negative 300,000, right? So either way, if I divide by a number that's close to 0, my answer will be either super positive or super negative, right? That's why deciding if the top and the bottom are positive or negative really matters. The top is negative, the bottom is negative. My overall answer should be positive, but since I'm dividing by something close to 0, my answer should be a positive extreme number, which I will write as infinity, right? This is bigger than any positive number I can come up with, and that's what we write, okay? Similar argument here. X is approaching -1. A number close to -1, minus 3, is an overall number close to -4. Oh, that number and that number are the same number. They're not 0. I can just cancel them out, and I will be able to simplify the limit to this. Very similar to the situation we were in before. What's the difference now? X is still close to -1, so a number close to -1 minus 2 is overall close to -3. This is a negative number. On the bottom, because x is a little bit bigger than -1, a little bit bigger than -1 plus a full 1 gets me a positive number on the bottom, kind of like that analysis. So if I take a negative number divided by a positive number, my answer is negative. But the fact that I'm dividing by a number close to 0 means I'll be a very, very deep negative number. I write this as negative infinity. So it's more negative than any number you can write down. All right, let's just glance at a graph real quick and see if we can reconcile this with the previous example. So I've got in here this function, and I'm going to hit the graph button. And we're going to look at what happens as x approaches -1. Boom, there's a vertical asymptote. Okay, so as we approach -1 from the left, so this way, oh look, the y values go up to huge positive numbers. We write the limit is equal to infinity. Then if we approach -1 from the right, so we're approaching this way, oh, the y values go deeper and deeper into the negatives, we write the limit is -infinity. So this is how the algebra matches up with the graph and the visual logic we had before. Okay, to recap. When you're taking limits, often the first line of defense is to just take the number x is approaching and plug it in. See if you can get a value. In this case, we realize we are dividing by 0 when x is -1, so we don't get a value. Factoring will help us understand what's going on. So we factored it. Then we said, as long as x is close to -1, this part doesn't matter. In fact, you identify that this behavior is going to give us a hole in the graph, a removable discontinuity. Okay, so that's out. We just look here, and now our focus is, as x approaches -1, the denominator gets very close to 0. We're dividing by a number very close to 0. So we're going to get an extreme result, a very big positive number, or a very, very negative number, right? So we want to identify if the numerator and denominator come out to be positive or negative, and then use the logic of negative number divided by negative number is positive, but since we're dividing by close to 0, our answer is super positive. We say the limit is infinity. Similar analysis down here. Okay, now let's get to this guy. So as x approaches 3, now the issue is, since we're getting really close to the 3 here, we have to think, does that affect our ability to cancel this factor out of the numerator and denominator? Oh, it doesn't. Wait, why not? Because x is close to 3, but not exactly 3. So still, we're safe. That number is not 0, that number is not 0. We can just cancel them out. So this is simply the limit as x approaches 3 from the positive side of x minus 2 over x plus 1. Now let's attempt to take this 3 and plug it into the numerator and the denominator. So that's going to be 3 minus 2 is 1. 3 plus 1 is 4. Wait, is that just 1/4? In fact, it is. Wait, what's going on in the graph? At x equals 3, so if I hit the trace button and I punch in x equals 3 and I hit enter, there's no y value associated with that. Why not? Because when x equals 3, I have 0 over 0. Right? That's the hole in the graph. That's our removable discontinuity. So there is no y value for the graph. As in, f of 3 does not exist. It is undefined. Okay? But if we take a limit, we're saying what does the y value get close to as the x value approaches 3 from the right? Oh, well, we're just getting to the location of that hole, which amounts to saying, well, if x is not exactly 3, this part and this part will safely cancel, and what's remaining, that's our lookalike function. That represents the shape of the graph everywhere else. So if we just look at where that graph is when x is 3, we get the location of the hole. That's sort of what we're doing in the graph. Okay? So if you try to take the value x is approaching, you plug it in, and you're dividing by 0, you want to factor to see. If you get 0 over 0, as in the case here, right? If you plug in literally 3, you get 0 over 0. That's indicative of a hole-like behavior. And so we can simplify, get a limit. Great. If we get 0 on the denominator, but not the numerator, so just 0 on the bottom, that is indicative of a vertical asymptote type behavior. And that's when we have to think about this positive infinity, negative infinity case. And how do we do it? We assess if the numerator and denominator are negative or positive, and decide based on that. So now that our toolkit includes the ability for a limit to equal infinity, we can start talking about a combination where we look at end behavior. So the limit as x approaches infinity, the limit as x approaches negative infinity, and see what happens to these things. Okay. So this x squared plus 1, we know what that looks like. That's just a parabola with a y-intercept of 1. All right, so this is y and x, and something like this. It goes up like that, and it goes up like that. Right, this is the y is equal to x squared plus 1. Well, the deal is, as x goes to really big positive numbers, what happens to the y values? Oh, they just keep getting bigger. So we say, as x goes far out to the right to really big positive numbers, the y values also go to really big positive numbers, and they don't approach any single number. But we have the ability to then say this, we can write is equal infinity. This gives us more tools. Okay. Similarly, this natural log x situation. So what does the graph of natural log x look like? Well, we know that there's a vertical asymptote at x equals 0. It sort of does this. Has an x-intercept at 1, 0, and then it does this. Now, certainly, it increases very slowly, and more slowly as the x's get bigger, but does it ever get to a maximum value, or does it keep increasing forever? Well, it turns out it keeps increasing forever. And you can think about this as the inverse of the e to the x function. I'm not going to deal with that right now. I'm just going to assume that you remember what natural log x does. And so the argument is, as x goes all the way out to the right to huge positive numbers, the y values keep getting bigger and bigger, and they just always keep getting bigger and bigger. They don't approach any single number, but they're always bigger than any number you can pick. Oh, equals infinity. Similar logic here. Okay, so remember, last time we wrote down something like the limit as x approaches infinity of e to the negative x. And we said that this was equal to 0. And we also said the limit as x approaches negative infinity of e to the x is 0. And we said these two things were the same as each other. This isn't quite this. It looks similar, but notice a difference. This time x is approaching negative infinity instead of positive infinity. Okay? Let's think about the graph of y equals e to the negative x. So we understand that there is a very steep part here. Our y-intercept is 0, 1, and we go and we have a horizontal asymptote at y equals 0. This is the y is equal to e to the negative x. So what happens as x goes toward the left? Oh, the y values keep going up. This is another example of infinity, which means, and I'm going to switch to writing in pencil here, okay? So here we go. The limit as x approaches negative infinity of e to the negative x is infinity. What if I wrote the limit as x approaches positive infinity of e to the positive x? Okay, think about it this way. X is a negative number and a very negative number. Negative times negative is a positive number, and that's going to be a big number. E to the big number. Oh, we talked about this before, right? Because e is like 2.72-ish. When you take that and raise it to a big positive number, the answer is a huge positive number. So as x gets very big, e to the x also gets very big. Okay. Now, which of course raises the question, hey, I have a bunch of examples where many, many times this end behavior is positive infinity. Is the answer always positive infinity when you put something like this? No, I just came up with examples where the y value was always increasing. I could have just as easily done the following and said, what about the limit as x approaches infinity of, okay, what if I said negative x squared plus 1? What would this have done? Well, the parabola would be now upside down. So it would look something like this. So as x goes way out to the right as x approaches infinity, the y values are going to go way down into the negatives. So we would say this is negative infinity. Okay, so you do have to look at it on a case-by-case basis. And of course, there are certain things you could memorize to make your life easier, but I think one of the most valuable things you can do and teach yourself to do is to graph at least all the basic function types, partially from memory and partially from logic, and then try to match your visual understanding with the algebra that you're writing down. And I promise that will help a lot with a lot of these problems. And let's write down some symbols at the end. Just a bit more discussion, right? Because we have to address some technicalities. So this was the basic definition of a finite limit. So x is approaching a finite number, and we say that the y values are approaching a finite number. Okay, not going to go over all the logic again. That was the base case. But now we have this thing where I can say the limit as x approaches a number of f of x, and I can write equals infinity. Now, keeping in mind, infinity is not a number, right? So I can't say, like, f of 5 equals infinity. This is just not a thing I can do, right? So either f of 5 is a number that I can write down, or f of 5 does not exist. It is undefined. You will never write that a number is equal infinity, right? You also can't say, like, infinity equals infinity. You can't say dne equals dne. Like, things that don't exist or aren't numbers can't equal other things, okay? That was the deal. But here's the problem. After all that, I'm still writing equals infinity. And it's because, specifically in the world of limits, we have decided that this is how we're going to write it with the equals infinity to indicate a very specific behavior. This is what I mean. If and only if, right? For all, instead of epsilon here, I'm just going to use a different symbol, n. For all n greater than 0. And you might remember my use of n when we had the limit as x approaches infinity. So we're going to imagine this n as a big positive number, okay? There exists a delta greater than 0 such that, okay, as long as the difference between x and the number it's approaching is less than this delta, then f of x is bigger than n. So, on technicality, what's going on? We were talking about here the y value is getting close to L, meaning the difference between the y value and this limit number, that difference is going to be smaller than a number I pick. So I'm thinking about, small differences in the y value. Over here, I'm just saying, no matter what number I pick, I'm able to say the y values are bigger than that number, as in the y values are going up indefinitely. That behavior, like we saw in a vertical asymptote, is what we mean when we write that this limit is equal to infinity. And a similar thing exists where the limit is equal to negative infinity. But I really want to drive home the point that just because we're writing this does not mean we're saying this limit is a number. It does not mean infinity is a number, because infinity is not a number. It does not mean that you're allowed to write number equals infinity. Okay. The equals infinity notation is a very specific thing to limits that we, or I guess our ancestors, decided to establish in order to indicate this vertical asymptote-like behavior. Okay. Does this matter to you right now? Maybe not. But, once again, it's a trust me bro kind of thing. And maybe, there will come a time in our future where we do get to sit down and go through a lot more of these formal things and prove, I guess, things with them. Well, thanks for tuning in. Hope you enjoy the rest of your day. Take care. I'll see you next time. Peace.